So I'm going to tell you a little bit about spectroscopy of graphene in water. But before I do that, I want to acknowledge Yongkang, Taka, and Yuki, who did a lot of the surface spectroscopy, and Xiaoqing, and especially Nikita, who's here in the audience, who pioneered the graphene water friction. So I don't think I have to motivate why we're interested in nano-confined and interfacial water. You know, we usually describe it as a continuum, but certainly that continuum description must break down when we go to small enough scales. And it's clear that those scales are important, but not very well understood. And so today I want to talk about the graphene water interface. And in particular, I want to talk about, electrochemistry, and that gives rise to proton tunneling and a new type of memristor, and about how can we look at the interaction between water and graphene when water flows, and how can we interrogate those interactions that also give rise to friction. So how do we want to watch the water, right? And so how do we do that? Well, we do that by using vibrational spectroscopy. So water molecules are, right, 2 hydrogen atoms and oxygen atom. And water molecules are very happy. They're cheering all the time, and they can cheer symmetrically or asymmetrically. And the frequency with which they cheer depends on the strength of the interaction with other water molecules or with whatever it is they're interfacing with. And so a strong hydrogen bond leads to essentially a weakening of the original OH bonds, and that lowers the vibrational frequency. And so there's a correlation between the frequency in wave numbers and the oxygen-oxygen distance in water. This is a well-known correlation. And that means that inversely we can use the OH stretch vibration as a marker of the local water environment. And I'll show you how this pans out. Now that's nice, and it allows us to look at bulk water systems, but we're interested in the 1 or 2 or 3 layers of water that are at the interface or in confinement. So how do we map the vibrational density of states of those water molecules? Well, we can do that using this technique called some frequency generation, which does exactly what we want, gives us what we want. And the technique relies on irradiating a system with an infrared pulse that makes the water molecules very happy. And then we can upconvert that happiness with a visible pulse. So this is the vibrational transition, and we can upconvert it to generate the sum frequency of those 2 fields. And when the IR is resonant with a molecular vibration, we get more of this new light coming from the surface. And as with any spectroscopy, this spectroscopy has selection rules, and I don't want to go into too much detail, but the selection rule of SFG is that the symmetry must be broken in order for this process to occur. And that means that it gives you a finite signal at an interface where symmetry is inherently broken, but in the centrosymmetric bulk, it's a forbidden spectroscopy. So we don't see the bulk. It can be there, but we simply don't see it. And to illustrate that surface specificity, I show you here this is now the imaginary part of the susceptibility. Again, I don't want to bore you with too many details, but it has a positive sign and a negative sign. That's because the symmetry is broken, so molecules, OH groups, can point up or down. And you see that the spectrum looks quite rich. So there are hydrogen-bonded groups that point downwards, and there's this very high frequency OH groups that point upwards. And so we can easily assign these high frequency modes. They're not hydrogen-bonded. They almost have a gas phase-like frequency to OH groups that are sticking out of the surface into the air, are not interacting with anything. And these hydrogen-bonded OH groups are these guys here that point downwards at the interface. So it's very surface specific because, of course, these free OH groups don't exist in bulk water. So if we compare it with the bulk infrared spectrum, that looks quite different. So let's then apply this technique to our graphene water system and try to investigate some electrochemical effect. And so there's basically two effects that we were interested in. The first is the physics of this interaction. So if we apply a potential to graphene and we align the water, do we align the dipole, or do we get, for a negatively charged, a hydrogen bond with the surface? So is there some asymmetry? From the chemistry point of view, the question was, how does the chemistry occur at this interface? So then we really use graphene as an electrochemical electrode. And in principle, you can separate these two regimes, the physics and the chemistry regime, by just, for the physics, if you stay at low enough electrochemical potential, you should not be driving any chemistry, and you should just see the physics. But as we increase the potential, we should start seeing chemistry. And this is just a textbook electrochemical IV curve, so the cyclic voltammetry, for those of you who are familiar with it. And so what you see here is that if we decrease the potential, in this case of platinum, you see that the electrons that are in the platinum find protons to generate hydrogen, and you get these hydrogen bubbles. So it's electrons from the electrode with protons from the water. And so this is the hydrogen evolution reaction. That's what is causing this large current. But if we go to this regime where we have almost no current, we see that we're in this what's called the capacitive region, and you see that the current is now very small, so it's microamps, and this is termed as the sort of the physics region of the response. So there is a small current that depends on, it's hysteretic, it depends on how you change the current, and this is due to ion adsorption and dipole orientation. So it's just a capacitive current that runs. So we make our sample by putting graphene on a calcium fluoride plate, and of course we need to get the electrochemistry right, so we have the graphene is the working electrode, and we have a reference and the counter electrode as well. And then the calcium fluoride allows us to do SFG and address this interface here with between the graphene and the water. And this is one of our CVD graphene samples here. These are the gold contacts, and you can see that we span this whole macroscopic region and we have good conductivity. So if we do the SFG, we get something that looks, if you look through your eyebrows, kind of intuitive. When we have a positive potential, the OH groups are pointing down, which is what one might expect. So it looks like this, so these are pointing down. If the potential becomes negative, the OH groups are pointing towards the graphene, and so this is somewhat seems intuitive. There's, however, a couple of buts. The first but is that this response of the water seems extremely nonlinear. So it's oriented, 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 and then suddenly it flips, and it then remains oriented. So it's a very sigmoidal curve. And the second thing is that at a high frequency, we see this negative OH band, so it's pointing away from the graphene, but it's not hydrogen bonded, which is very odd because there's water on that it should interact with. So it can't be this guy that's pointing towards the graphene because it has the wrong orientation. So what's happening? Well, let's take a step back, and one of the things we have to realize is that if we put water on a substrate and we put graphene in between, the water doesn't care. So graphene doesn't shield the charges on the substrate very well. And so if you measure the wetting angle, in these two cases, it will be almost indistinguishable. And so what that means is that we have to consider both the charge on the graphene, which we're controlling electrochemically, but also the charge on the calcium fluoride on our substrate, and that may change. as we change the system. And so the charge on the graphene we can simply measure by doing Raman spectroscopy, and this behaves very nicely. So you see that the charge density on the graphene changes linearly as expected with the applied potential. So this is all very intuitive. We can determine the total charge density, this gets a little bit technical, by measuring the water response at different electrolyte concentrations. And again, I don't want to bore you with the technical details, but I hope you will trust me when I say that we can measure the net, the total charge density, and you see that this has this sigmoidal shape that I told you about, which means that if we take the difference between the two, this is what is happening to the calcium fluoride. And so it's really what we're seeing is a change in the calcium fluoride charge density and not so much a change in the graphene charge density. Now, what this means is, so first that the water is dominated by the calcium fluoride, but that somehow changing the potential discharges and charges the calcium fluoride, which means that there must be chemistry going on because the surface potential changes by absorption of hydroxide or protons. So that's the only way it can happen. And in some way, this is not a ridiculous concept because I told you that protons can take up electrons from the graphene to generate hydrogen. And so that can change the pH because when protons are used up, we're left with hydroxide ions at the surface. But that means that somehow the pH change on this side of the electrode must be able to be transmitted to the calcium fluoride somehow. And we know that we have a few monolayers of water between the calcium fluoride and the graphene. That's inevitable when we make our system. But how can there be equilibration of pH on this side and the few water molecules that are here trapped between the calcium fluoride and the graphene? Well, that is, of course, something that you will hear more about later today. Protons can tunnel through graphene, as is shown here in this cartoon. So here's the H3O plus that with its different hydrogen bonding arrangements, this proton can hop to this water molecule. So now the hydronium ion is here right at the interface, and then this proton can tunnel through to become this hydronium ion on this side, and so now we have pH equilibration across the graphene. And so if this is all true, if the local pH change accounts for our observations, then what we should be able to do is simply take our potential off of our graphene, change the bulk pH in front of the graphene, and do the measurement and see whether we can correlate a certain potential, electrochemical potential, with a certain pH. And we can. So we can always find a certain pH, reasonable pH, that reproduces precisely the measurements we do at different electrochemical potentials. So really what we're seeing is not physics, we're not seeing water reorienting to charge, we're seeing electrochemistry happening, and that changes the surface charge of the substrate. And that also explains this funny peak here at very high frequency that is not strongly hydrogen bonded and that points downwards, because what happens when we increase the pH, so when we produce hydroxyl ions on this side, we get hydroxyl ions on this side of the graphene, and they adsorb to the positively charged calcium. So you get calcium OH groups, and those have this frequency, and they point downwards. So that all makes perfect sense now. So we understand what's happening, and you might shrug and say, okay, well, so you have a very fancy schmancy way of looking at electrochemistry. But the interesting thing is that we are seeing this huge change in pH, and it's not small, right? It's 5-6 units of pH change. It's really quite dramatic. And all of the pH change is happening in what is nominally this capacitive regime. So where textbooks tell you there is no chemistry occurring because the electrochemical potential is not high enough. And we see that there is electrochemistry occurring. And so when we had this result, I called my friend Mark Koper, who's an electrochemist at Leiden University, and I told him, Mark, you know, this makes no sense. Like, we're seeing chemistry where it's not supposed to happen. And he said, oh, that's so interesting, because when we measure the capacitance of our electrochemical cell, we always measure something that is larger than what is expected from simple theory of ion adsorption. And we call it the pseudocapacitance, and we don't really know what it is. There must be some chemistry going on, and you've now discovered the effect of pseudocapacitance. So that was very nice. So can we use this proton equilibrium? And so now the next part of my talk is completely following in the footsteps of Lydéric. And so can we use the transfer of protons to make a memristor? And so a memristor is nothing other than you have a device, you apply a potential, and the conductivity through the device depends on how it was treated potential-wise in the past. And so Lydéric has a very nice paper that shows that for an ionic channel, a nanofluidic channel, where you see exactly this effect. So you see that depending on where the voltage comes from, the conductance of this channel shows a different behavior. So you have, at a certain potential, you have two distinct values for the conductance, depending on where you come from. So this is a wonderful paper, and it inspired us to look at our system, and not using, this was, I think, calcium, using as a ionic memristor, but using protons. So protons are, of course, ubiquitous in water, they're everywhere, and protons are actually also a neurotransmitter. So if you're thinking about biointerfacing, that might be useful. And so the idea was then, basically, we call it a chemimemristor. So using the current to change the conductivity by the electrochemistry that we're driving, by changing the pH. And so by changing the pH, we change the charge on the calcium fluoride, and we also know that if electrons are moving through the graphene and there's a charge nearby, it will scatter. So this will have a lower conductivity than this case here. Well, here there's a negative charge, but suppose this were neutral. And so this was the idea, and this works quite nicely. It's not as dramatic as the calcium-based memristor, but you see that there's this hysteresis in the conductivity, and this hysteresis actually, when you correct for the charge density in the graphene, so we're of course changing the Fermi level in the graphene when we apply potential. If you correct for that, you can see that there is a larger hysteresis in the electron mobility of the system, and you can do this at different potential scan rates, and you can see that over a wide range of scan rates you have this hysteretic behavior. And so the reason for that is really quite simple. When we apply a positive potential, the surface is positively charged, and so we have a relatively low mobility. And then as we increase the potential, go towards negative, we start making the OH minus. The OH minus adsorbed neutralizes the surface, and that increases the mobility of the graphene. And so we can then try to correlate the mobility that we observe with the water signal, because the water feels this charge, right? I just showed you. And that we can indeed do. And so we can get the charge density from the water signal, and so at positive potential there is a relatively high charge density, and so this is 1 over the charge density, and then we have a low mobility, and as we decrease the charge density, we see the mobility go up. So it's a very nice and simple memristor that doesn't. It's just putting graphene on calcium fluoride, and then we can play all the games with pulsing potentials and that all works. But I don't want to go into that. So the summary of this first part is that there's a lot of chemistry going on where you wouldn't expect it, where you would just expect physics, but we can use that chemistry at moderate potentials to make a not very good but a very simple memristor. So I want to finish with one of, I think, Lyderic's favorite topics, quantum friction. And of course, Lydéric has shown very nicely that water flowing through a nanotube is very different from water flowing through your average garden hose. And so Lydéric and Marie-Laure and Nikita, who are all here, basically inspired this work, and Xiaoqing did some of the experiments. And so I think I'm preaching to the choir here, but let me just very quickly summarize. So very different slip lengths for graphene and graphite, a radius-dependent slip length on the carbon nanotubes, and these are all materials with the same physical corrugation. So there's no reason to assume why the friction would be different. And so classical friction theory cannot explain these variations because the corrugation is the same. And so if we have just classical balls bumping into a rough wall, there should be no difference. And so something is missing, and that is what Nikita and Marie-Laure and Lydéric so very nicely described in their Nature paper in 2021. And they propose that there should be electronic effects. So it's really, you have an electron bath in your substrate. The water has a very large dipole and has very large transition dipoles that can couple to this electronic system, and that you can calculate an electronic friction force that is related to the surface excitation spectrum. And so it's friction through electronic excitations. That is my sort of one-slide summary of this very complicated paper. And so you can then, and this is all paraphrasing from Lydéric and Nikita's and Marie-Laure's paper, you can then cast the friction coefficient, or the friction per unit area, in a classical and a quantum term. And the classical term is just what you expect it to be, right? It has a surface roughness and the structure factor of the water. And the quantum term has this overlap integral of electronic excitations and water excitations. So it's really this electronic friction effect. And so in this particular case, they argue that it's the Bayer modes, so the low frequency water modes, collective motions, dipole reorientations, that couple to the surface plasmon mode of graphene or graphite. And because graphite has not only in-plane plasmons, but also out-of-plane plasmons, it has a higher electronic friction coefficient. So this was all theory, but how to prove quantum friction? And this is where Nikita came up with, actually, he just reinterpreted data that we had that we didn't understand. So I wish I could, claim some credit here, but I really can't. But the experiment that we did to try to prove this is, again, graphene in contact with water. And the idea was, and there's a slide missing here. Oh, there is a slide missing here. So the idea was that if you have this type of momentum transfer, so you have a mismatch in the velocity at identical temperatures of your two subsystems, so this is the liquid, this is the solid, Nikita showed that that is equivalent to having no velocity mismatch, but a temperature mismatch. So you can recast this friction term into an energy flux term. So momentum transfer basically implies energy transfer. That was the thinking. And so the idea was to then create a quasi-instantaneous temperature mismatch between the electronic system in the graphene and the water system. And we do that with an by optically exciting the electrons in the graphene, so that causes a quasi-instantaneous temperature jump of the graphene electronic system. And in the absence of any liquid or water, the hot electrons cool simply by phonon emission. And they do that in a few picoseconds. And so we can read out the instantaneous electron temperature with our terahertz pulses. And again, it's not so interesting to go into the details, but it's really just a transient absorption measurement, and the attenuation of the terahertz pulse, which is also very short, gives you a direct measure of the electron temperature. And so the experiment is then very simple. Then we do this experiment without water, measure the cooling time of the electrons, and then we put water in and see if there's a speed up of the electron cooling. And so the idea now is that we couple to higher frequency modes, so in the order of tens to 100 millielectron volt, because now we need to transfer significant amounts of energy. And those low frequency modes of those different liquids that are shown here then couple to the graphene plasmon, and you get this kind of overlap, this product of those two. And so this is what a typical measurement looks like. So we have the cold electrons, we heat them very quickly, and they cool on the time scale of a few picoseconds. And so the idea is that the heating process is very quick, so there's very strong electron-electron interactions in the graphene. And so we can define very quickly a temperature of the electron bath. And so then we did the same experiment. So in nitrogen, then we added different liquids in front of the graphene. And if you look very closely, you can see that isopropanol is in purple, is the slowest, and the water is the fastest. And it's a subtle effect, but it's, of course, we've reproduced it and we measured it many times. And then you can, from these single exponential fits, you can simply get a relaxation rate that it has a certain value of, so it's 2 picosecond relaxation. And when you add water, it shoots up by about 20% or so. Interestingly, when you replace the water by heavy water D2O, the effect halves. So that was very surprising. And when you go to isopropanol, actually there's additional slowing down, which we assign to screening of the electron-electron interactions and electron-phonon interactions. So can we understand this? So first of all, this was like, yay, we see it, so now we understand our data. In other words, there is a speed up of the electron cooling when there's water present. So there is a clear indication of energy transfer from the graphene electrons to the water in line with this quantum friction theory. So can we understand this polarity dependence, and can we in particular understand this isotope effect that we see? And so Nikita did his thing and did his calculations, and he showed, so in red is the experimental data, and he calculated the contribution from the flux of energy going into the liquids, and you can see that there's, I would say, semi-quantitative agreement, so the values are in the right order of magnitude, and certainly the trend is fully reproduced. And I should stress that there are no adjustable parameters in this calculation. So that is great, but why do we have this trend, right? Why does it look like this? And so this is where I come in. I can do I can do very simple things. So this is the expression that I failed to show before. This is the power per unit surface area transferred. And this is this overlap integral, essentially, between the water density of states and the graphene electron density of states. And so the graphene plasmon and the low frequency modes of the water, and it's basically the product of those two that determines how quickly there's energy transfer can occur. And if you look at the graphene plasmon, well, that's kind of featureless, right, in this energy range. So what is responsible for the strength of the interaction is really the low frequency modes of the liquids. And so I did a very complicated calculation. I integrated the low frequency regions of all those different liquids and then plotted what Nikita had calculated against the integrated spectral density, and you see that I get a very nice simple correlation. So this is completely consistent with the notion that it's the density of states at these low energies of the liquids that allows the electrons of the graphene to relax more quickly. So Nikita has dubbed this electron-hydron coupling. So the conclusion of this second part is that we can see experimentally by looking at energy transfer evidence for the momentum transfer, for the friction, and this was all done by Nikita, and the paper is in print. So before I conclude, I want to show you one thing that I promised actually I would show when I looked in my abstract, which is spectroscopy of nano-confined water. So what I showed you so far is all basically interfacial water. So it's bulk water in contact with graphene. But we can trap, as I told you, a few water layers between calcium fluoride and graphene. We can't vary the thickness, so it's just what we get. It's about a nanometer, and we can do the spectroscopy on that, and you get very interesting wiggles and jiggles, so negative, positive, negative wiggles and jiggles of the water. And actually, and you can compare that to the water-air interface that I showed you before. And actually what we find is that we can describe this purple line very reasonably by a linear combination of two interfaces, namely the calcium fluoride water interface here in red, and in blue the graphene water interface, which we measured independently by putting a flake of graphene on water and measuring the interaction. And you see that, so this negative peak here is now this OH group that is interacting with the hydrophobic graphene. And you see that this negative positive wiggle comes from the negative contribution from the calcium fluoride water interface and the positive contribution in the hydrogen bonded region from the graphene water interface. So this is very preliminary data, but I wanted to show it to you. It's possible, we can do it. We can measure nano-confined water, and so this appears, so as a first approximation, we can even, for these very thin layers, we can approximate this as two nominally independent interfaces, which to me was a surprise. So with that, I'd like to thank you for your attention and thank Lydéric for the kind invitation. And if you ever want to build your own water, be careful. Thank you.